All right, hi. So this is going to be lecture 19, and it is on elastic plastic fracture mechanics. So this is still based in chapter 3 of the textbook, and it's the last concept we need to cover before we can talk about low cycle fatigue. So we talked in the last lecture about predicting whether we would have a catastrophic failure due to rapid propagation of a fracture. And we used linear elastic fracture mechanics, and we calculated a fracture toughness, and then what we did was we compared that with the characteristic fracture toughness for a particular material. And so we had to make a few assumptions that went along with that. I have to tell you, unfortunately, this lecture, I do not have the capacity to use my stylus, so it's going to be slide-based, but I will explain every part of the slide as though I were writing it. So we had to make some assumptions. The first one was that we're in a plane strain regime, which means we have a relatively thick component that allowed us to make some assumptions about the stresses in the crack tip. And we assumed we had a very small plastic zone, so that when we were pulling on a specimen, like sort of far away, we don't have to worry about plastic deformation. We can assume the whole thing is elastic except for right at the crack tip. And we just kind of say that if stresses into this fracture toughness go above the critical fracture toughness, we would expect failure. And so that is good. But for practical applications, we may not have materials that have that high of a strength, right? So in practical applications, we may have low strength or medium strength steels, and the sections are too thin to assume plane strain. So we may have like a pressure vessel, thin plates, something like that, that are riveted together. And so we can't make that assumption anymore. And when we do that, that means that the plastic zones at the crack tips can be quite large. And so we can't assume that those plastic regions are very small compared to the rest of the material. And so that's where we come in with elastic plastic fracture mechanics. And we're going to talk about a J-dominant regime today instead of a K-dominant region. So when we're in a K-dominant, that's the small plastic region and high strength material and thick material. And so we will use a different method to think about thin materials, big plastic regions. And we're going to end today on something called a failure assessment diagram. And we'll walk through how that allows us to check for both brittle fracture and plastic collapse, assuming a big plastic region around a crack tip. So sorry, there's going to be a lot of words on the slides today that I would have normally have written all of them in class, but I'll point out what the most important things are. So when linear elastic fracture mechanics is valid, then we have this equation here, and I'll just go through this briefly. So we know what K is, right? K is the fracture toughness. And if we take that and square it and then multiply it times some material properties, so Poisson ratio, elastic modulus, that gives us an energy per unit area, or you can think of it as force per length, but it really is an energy per unit area. And that is going to be equal to what Griffith studied quite a bit, which is an energy release rate. And so when there's a crack, so imagine there's an edge crack like we've been talking about in class, and then there's a stress that wants to open that crack in mode 1. Well, there's a strain around the crack tip that exists just because of that stress. And so when the crack opens further, that strain energy is relieved, right? And so that is the basis for this G, this strain energy release rate. And then what Griffith did was also he collected that and he put that together, that strain energy release, with the stress state around the crack. So that's this J. And then there's also some further work on thinking about this crack opening displacement delta with respect to the yield stress. But we're going to ignore that part for today. We're just going to talk about J. And so we know that when the crack opens, then there's strain energy released. And so that strain energy released must also be balanced with what's happening in the rest of the material around the crack. So that's the origin of this J integral, or what's shown here in the middle of the screen. So the J integral is a path, an integral around a path in space around the crack tip. So I'll just show it on the next slide here. So if we look at this in 2D, here's our crack. It's in a large plate. And we're going to choose an arbitrary path, right? In this case, the path is not even circular or anything. It's just a random walk. And we'll represent that path by this uppercase gamma, a small, infinitesimally small portion of the path, ds, and then a force, in a lot of cases it's a traction force, so we call it T, on that little space there. And so the J integral is a line integral around that path, and it's a difference between the traction over those infinitesimally small things and the load work per unit volume, so what work is being done externally. And so if we subtract those two, we should get J, which should be equal to that strain energy release rate G. So that's the J integral, and there's a lot of fundamental work done in this area to prove that that is true. And so we're not actually going to calculate the J integral because that would require a significant weeks of computation to figure out how to do that. But I just wanted you to know the concept of this J integral and where it comes from, so that when we go into like a few more empirical ways of thinking about crack propagation, you know that there is some fundamental work that's gone into thinking about how the energy is released in that material and how this strain energy release rate G and subsequently J are constants when linear elastic fracture mechanics is valid. And they are directly proportional to the square of these material properties times the the fatigue strength K. Okay, so this is a slide with a lot of words that I said a lot of them already up front. And so really what they showed is that when the J integral for any arbitrary path around a crack supersedes the J integral that is critical, or a critical strain energy release rate, then we would predict that this crack would propagate. And so this is what they did for cracks. When I just remind you, these are that have elastic plastic conditions, when those conditions prevail. So when it's not a K-dominant regime, but a J-dominant regime where there's a lot of plastic deformation. Okay, so that is helpful sort of in a fundamental sense. We can, if you are the fundamental type, you can go play around with this and calculate things. Did you have a question? You mean put G in this equation here? Only, so the question is, for those at home, the question is, if the other equation is true, this one, 359, can we substitute and say that G is equal to, if that surpasses a critical J integral, then we could say that cracks will propagate. So unfortunately in this case, no. This G is only equivalent to J if linear elastic fracture mechanics is valid. So this is like the simplified case where we can say this is equal to this is equal to this, like everything aligns well. But when we get into a case that we can no longer assume linear elastic fracture mechanics, we might have to assume nonlinear elastic or elastic plastic fracture mechanics, then we can no longer say that all these equivalences hold. So that's why the J integral was expanded and done on cracks that had a large plastic zone or were on thin materials.
So that equation only allows when there's no linear elastic.
Right. Yep. So if we can't make a plane strain approximation and linear elastic fracture mechanics is not valid, we can't say all these are equivalent. Okay. So the transition out of this now, talking about the J integral, is that if we need to design a system and then say, okay, what's going to happen if there is a crack in that system, we cannot, we can't do a J integral around that crack every time. We just have to sort of inspect the crack and make a prediction to know if that will be a stable crack or not. And so that's where some further modeling came in. And so I'm going to talk about this short model here, which is more of a conceptual model, but it allows for some quantitative approximations, which is helpful. So this model is called the Dugdale-Barenblatt strip yield model, and you can see it represented here on this 2D plate. So before we had a crack tip, right? So this is a center crack through the thickness of a plate. And before we said that there might be a plastic region at the ends of that crack, but the plastic region was like a circle that we drew around, and we said, here's kind of where there's probably some plastic deformation based on stress concentrations. And so we can say that because we don't really care what the shape of that little plastic region is. If we're doing linear elastic fracture mechanics, we're far away from the crack tip anyway. But when we have plastic deformation, we can't do that. And so these researchers came up with a model that is represented here. So here's the crack. It has all the same dimensions that we had before. So we had A, we have stress pulling on it. But rather than have a circle and try to approximate what's happening there, they call these plastic zones basically strips that are acting with stresses perpendicular to the orientation of the crack. And at the crack tip, they said, okay, if we know that this is going to basically be yielding, we'll just assign and say that the yield stress, so it says sigma yp there if it's too small to read, that the yield stress is acting at those crack tips in this kind of geometry. And it extends in, this is where some of the approximations come in, it extends in some distance rho, or little p, in from the end. And so that is a hand-waving kind of assumption that you need to make in order to apply this model in any kind of quantitative way. And so what they did is they said, okay, if I assume the yield stress is acting on the sides of this crack tip, what I want to do is come up with a fracture toughness K that I compare with the material's fracture toughness. But I can't use the one from linear elastic fracture mechanics because it doesn't account for what's happening here at the ends of the crack. So what I'm going to do is a bunch of experiments, and with a bunch of different geometries here, and taking maybe a bunch of different distances here over which that occurs, and I'll come up with an effective fracture toughness. So K prime effective, it's going to be a function of the yield stress and the same term that we had before, square root pi a, and then it's going to have a bunch of geometric terms that are dependent on the stress that's being applied compared to the yield strength. So there's a sigma here, and then there's a sigma yp here. Okay, so we're assuming that this stress is less than the yield strength. So that fraction, we take the secant, the natural log, bunch of coefficients, square root of that, multiply it by this to get some effective fracture toughness. And as a first pass, we can just put in the yield point here because we can assume that yielding is happening here. But in a real instance, and what we know from basically chapter 6, is that we can put a tensile specimen in and pull it, or put a component under a 3D state of stress that continues to increase, and we can push it past the yield point into plastic deformation up to the ultimate strength, right? And so instead of using the yield point in this equation, a more accurate value to use would be what they're calling a collapse stress. And so that's this sigma c. And the sigma c is the average of, now this is also hand waving, the average of the yield strength and the ultimate strength. So we just take the average and say that on average, that would be the ultimate stress that it can withstand. And that so matches more with a lot of their empirical data. Okay, so the next slide is really crazy because I was going to build it up slowly. I apologize for that, but I'll point out to you just the overarching message, and then I'll build it up from there. So the these researchers, Dugdale, Barenblatt, they used this strip model, and then other people took it and said, okay, if I'm assuming this allows me to get an effective fracture toughness, I'm going to put together a map that tells me, what am I going to have a plastic collapse, right, this sigma C, if I do have a crack with plastic deformation on the edges, am I going to get that plastic collapse, or am I going to get a crack that propagates? And so am I going to get basically a collapse of this entire region, or am I going to get a crack that propagates across? Because both of those could happen in this situation. And so they put together what's called a failure assessment diagram. And it looks, this slide looks very crazy, but what I want you to pay attention to is this is a diagram that allows us to see where we are between two different types of failure. So the first one is going to be basically a plastic collapse through a critical stress. So this happens for materials that are very tough, okay? Materials that are very tough have sufficient ductility that they are unlikely to fail by brittle failure, even if they do have a crack. So there are some materials that just have a high enough strength to do that. And so that's one way that that could fail. And so we get up to that threshold by looking at the stress that's in a part. And so if we look at the stress that we have on our component and normalize it by that collapse stress, sigma C, that's the x-axis here. So if we are at the critical stress, this collapse stress, then this equals 1. And we would expect a failure, and it would have a fracture over the whole region, and it would be more of like the whole region failing. And so that's the x-axis here. And so it allows us to go from that point, that mode of failure, between that and another one, which would be a brittle crack propagation failure. And we don't look only at the stress for that. We have to look at the fracture toughness. And so on the y-axis here is another normalized value, 0 to 1. And instead of being stress, it's now the stress and intensity factor for brittle fracture, right, which is these K values, right, fatigue strengths. And so if we normalize the one that we have by that effective one from the strip model, and we go 0 to 1, then at 1 we would expect a brittle fracture to occur. And so what the strip model allows is the drawing of this line between the two. Okay? So if we apply what we know about fracture mechanics and then the equations on the prior slide, we come up with this equation here, and it's this Kr, so a normalized stress intensity factor, as a function of a normalized stress, this SRF. And so that term appears twice here, and that is the x-axis down here. And so what we can do is then inside the line, we have no failure. We not expect either failure. If we're outside the line and we're kind of close to this side, then we would expect a brittle fracture, or not a brittle fracture, a plastic collapse through the cross-section of the material. And if we're closer to this side, we'd expect a brittle fracture. And if we're in the middle, it really is a toss-up between the two. It's probably a combined failure mode. But this chart, this fracture assessment diagram, allows to check for both. Okay, so we're going to look at example 3 from the end of chapter 3 to demonstrate this. And so it says, I'll just read it out loud. Another 7075 aluminum tension member has been inspected, and a 0.3 inch through the thickness center crack has been detected in the 0.38 inch thick by 4 inches wide rectangular cross section. If this member must support a static tensile load of 50,000 pounds, predict whether failure would be expected. Use the failure assessment diagram to make the prediction. Also make an estimate of the existing safety factor. The ultimate tensile strength is 83,000 psi. Okay, so we have the geometry of the crack, we have some material properties, and so let's see what we can do to see what kind of failure would be predicted here. So first let's calculate that plastic collapse stress, sigma C, so it's the average of the yield point and the ultimate strength. So this is the same material that we had in the example problems from the prior lecture. So it has a yield strength of 75 kpsi, and then we'll average that with 83, which is the ultimate strength, so we get 79,000 psi. And then we want to calculate that normalized load. So what the stress is that we apply compared to the plastic collapse stress. We just calculated that, so that's our denominator. The applied stress is the applied load we were given, 50,000 pounds, divided by the cross-sectional area, which is the product of the thickness, 0.38, and then our width, which was 4, but minus the crack length. So we're not using the crack length. We're assuming that the load is carried outside of that crack. So if we do that calculation, we come up with a ratio here of 0.45. Okay, so that first tells us initially, if we go back and look at this, if we're at 0.45, like we're here on the x-axis, we're really not very close to this failure due to plastic collapse. So it's probably close to the other one. Whoops, wrong way. Okay, so let's keep going and see where we are. So we know where we are along the x-axis. So now let's see where we are along the y-axis. And so here we're going to calculate that y-axis, which was this normalized fracture strength or fracture toughness. And so we're going to have our fracture toughness for our problem divided by some normalizing value. In order to create that chart, they use this effective fracture toughness, that K effective from the strip model. But in this case, we have a tensile load, and so it really is a very simple case. And so we're going to use this K1C. And that's what they use in this book example. And so for a center crack tensile member, this is the equation for the fracture toughness. And if we wanted to include everything in the strip model, we could include that other term here off to the side. But for purposes of simplification, we're just going to use the K1C type equation here. So we have some geometric factor C, then we have our applied stress, and then we have a square root of pi times the crack length A. And so if we do A over B, which is half the crack length divided by half the width of the bar, it was 0.3 was our crack length, so area of 0.15, and 4 inches divided by 2 is 2. And so this ratio of A over B was 0.075. And that's what we used in those other charts with the geometry to find this factor, or find this coefficient C here. I don't have those charts in this presentation, so I'm just going to tell you that if we go back and look at them, figure 3.31, we would read off the chart a value of 0.975 for a ratio A over B of 0.075, solve for C, and come up with 1.01. So it's really not a big factor here. So then we can go back and calculate what our fracture toughness is. So this K1A, and so it's the C times our applied stress, so that was sigma A. So it's 50,000 pounds, divide by, and here they're just using the nominal. You can use the nominal or you can subtract off the crack length from here. So that's an approximate stress, times pi times crack length over 2. And so we come out with a fracture toughness 22.8 kpsi square root inches. Okay. So that's for our situation. And then we're going to normalize that by the K1C, which is 26,000. And so we get a value of 0.88. So that's going to be the y-axis on the chart that we had before. So if we go back to that chart here, right, it's actually already marked on here. So we'll go over to 0.45 and then up to 0.88. So we're right here where it says example 3 at point A, and we find that we are in the region of no failure. So, okay, very good. So this was a very similar example to the one that we did in the last class, where we used linear elastic fracture mechanics, and we were determining things like what's the load we can apply so that we would make sure that we don't have fracture. And so in this case, if we choose a load of 50,000 pounds, apply it to that same type of bar, And we do not assume plane strain, but we rather assume that there's a large plastic deformation because it's a little bit of a different situation. Then we would find that we do not expect failure. If the load continued to increase, however, and we took that into account, then we would eventually get up to this point here on the line that we drew from that strip model. And the difference between where we are and where we would experience failure gives us sort of an idea of a safety factor, right? So how much below this failure load are we? And so in order to calculate that, we could go up and see, you know, at what x and y we would expect to get failure, and then divide by sort of the distance to that point there, which we already know. And if we do that in this case, we get a value of 1.07. Okay. So it's just these two vectors that they drew on the plot there. And so we don't really have a very high safety factor. So if we go much above this 50,000 pound tensile load, then we would expect to get a crack propagation and brittle failure. Question? The safety factor in this case is going to be the distance that we have from the origin up to point A where we are, divided by the total distance we could get up to this failure curve. Does that make sense? Yes. So O to A divided by O to F. Yep. Yes. The question is the region of no failure on this side of the diagonal line also? And yes, it is. It's everywhere under this curve. I just realized I said the ratio opposite for this safety factor, by the way, so I'm going to backtrack on that and say that it's actually OF divided by OA is the safety factor, because it's more than one. Anyway, yes, this entire region under here would not expect to have failure. But you're always going to have some applied stress, so you can never be at the origin along the x-axis. But you may, in fact, get a brittle fracture if you have a low applied stress compared to the collapse stress, like maybe even 0.1, if your KR is really high. And so you can go back and think about like how this could be a design problem. Whoops, next, no, this one. If this KR is very high, like if the value we calculated for our fracture toughness gets close to the K1C, then this value would go very high and it would get close to a brittle fracture, even with very low loads applied. So it's kind of a balance between these two things that we're looking at today. So that's all I had for the lecture. I think it would have taken me a few more minutes to draw this all out by hand, but I did not have that capability today because I forgot to bring one piece of the equipment. And so that's where we're going to stop for today's lecture. And we'll pick up in the next lecture going back to now Chapter 8. Now that we understand a little bit how to consider plasticity when there are cracks, now we can talk about potential low cycle fatigue and plasticity under those conditions. So that's about it. All right, thank you.